Hey folks, so in the last video, we proved that the sum of two even integers is even. And the idea was to first write them using variables. So assume that you have, let's give your two even integers names, let's call them n and m. And if they're even, then we can apply definition 2.2. which says an integer is even if it can be written as 2 times k, where k is an integer. Of course, the variable name doesn't matter, so for n, let's use a, and for m, let's use b. It'd just be important to not use the same variable for both. You could use k and a or something, I don't know, as long as it's not the same variable for both. Because if they're both 2 times k, then that would have to mean, k is, once you've established it, it's fixed. So m and n would be the same thing, because 2 times k can only be one even number. It can't be two different ones. So anyways, so you establish some variable names, you apply the definition, and then you have to do some algebra, after which you can say, okay, so n plus m equals 2k. Oh, great. Therefore, by definition 2.2, it's going to be even. And here were the details. Basically, you say let m and n, so these are two different variables, and let's add them together. So let's add the two equations together, factor out a 2. Notice that a plus b is an integer. That's what fact 2.1 told us. And therefore, we can write it as 2k. Because it's an integer, let's call it integer k. And then boom, n plus m equals 2k, where k is an integer. Great. By definition 2.2, it's even. So anyways, if you want to catch the details of that one, go ahead and watch the last video. Now, let's go ahead and prove the next proposition, proposition 2.5, which says that the sum of two odd numbers is also even. Okay. All right, so here we go. Let's prove proposition 2.5, which says that the sum of two odd integers is even. So hopefully you watched the last video already and you've taken some time to actually sit down and try to, the proofs are going to be very similar, and try to write out a complete formal proof on your own of this fact. Okay, now here's the idea behind it. How do you prove that the sum of two odd integers is even? First of all, you give the odd integers names, call them n and m. Now that they have names, we can apply definition 2.2, the second part of it. To be odd means you're twice an integer plus 1. So for n, I call that integer a. For m, I called it b. So 2a plus 1 and 2b plus 1. And then some algebra happens. And the goal is to get down to the point where n plus m equals 2 times k. It's even. What does it mean to be even? It means you're twice an integer. And so therefore, it would be even. Okay, which is what we want to show. Make sense? So that's what we want to do. Give the variables names, apply definition 2.2, do some algebra, and then apply definition 2.2 one more time. Okay. So now over here on the right, I'll actually write up a complete proof. All right, so proof. Assume that n and m are integers. Sorry, excuse me, are odd integers. Okay, odd integers. So by the definition of an odd integer, definition 2.2, so by definition 2.2, we can say that n is twice some integer, I'll call it a, plus 1, and m is twice an integer, which I'll call b plus 1. And now in your formal proof, you should say what a and b are. Right? You've just inserted these letters. In your scratch work, it's fine to just throw letters around, but in your actual proof, make sure if you introduce a variable, you have to say what it is. In this case, according to definition 2.2, those are both integers. This for some integers a and b. So by saying some integers, all we're saying is we don't know what they are. I mean, we don't even know what n and m are. They're just some odd numbers. There are infinitely many options. But we know that there are some integers that you can put here to express n and m in this different way. Okay. Okay, good. Then comes the algebra. So just like in the last proof, our goal is to get down to say something about n plus m. Well, how are we going to do that? Well, we have two separate equations. Let's combine them into a single equation by adding the left sides and adding the right sides. Okay? And we're trying to get to the point where it's 2 times a single integer. So in the previous problem with the evens, our next step was to pull out a 2 from everything. But we can't do that right away because, I mean, these two terms have a 2 in it, but these two do not. Fortunately, the terms that don't have a 2 add up to 2, so it works out just fine. So this is now equal to 2a plus 2b plus 2. And now we can pull a 2 out, so that way it's 2 times something, and hopefully that thing is an integer. So this is 2 times a plus b plus 1. Okay? And this is great. A, b, and 1 are all integers, right? We know 1's an integer, and a and b are assumed to be integers. Therefore, by fact 2.1, we can say the sum of integers is still an integer. So it works out just fine. And since a, b, and 1 are integers, by fact 2.1, so is a plus b plus 1. Okay, so there you go. And that's great, because we've now shown that n plus m is 2 times a thing, and whatever that thing is, it's definitely an integer. That's what we just justified. So let's wrap this up. So we have shown that n plus m equals 2k, where k, if we set it equal to a plus b plus 1, then yes, n plus m does equal it, and moreover, k is an integer. So this is a way of writing that mathematicians sometimes utilize. And there you go. Therefore, we just have to apply definition 2.2 one more time. We've proven that n plus m is 2k. We want to show it was even, and according to definition 2.2, those are equivalent. Therefore, by the definition of even, or you can just say by definition 2.2, either one's fine, n plus m is even. And the dopamine hit, end of proof box. There you go. Okay, so there you go. That is proposition 2.5. Summing two odd integers gives you an even integer. And next, why don't you try on your own to try to prove that if n is an odd integer, then n squared, let's see, if you squared an odd number, is it always odd? Even? Yeah, odd. Always odd, in fact. Yeah, show that. Show that if you square an odd number, that you always get another odd number. 5 squared is 25, 3 squared is 9, and so on. So try to prove that on your own. Write out a complete proof that if you square an odd number, the result is still an odd number. And then come back next time, because that's the one I'll do on the board in the next video. All right, see you next time.